Welcome to the 20th office. We would like to tell you more about 20, but you are free to go to our webpage and learn a lot of things about it. We are always looking for people willing to do and to learn a lot of cool stuff. We are actually working a lot with the future of telco, which means a lot of things, and I'm not going to describe. Both over IP, integration with telco, fighting with telco, these kind of things. If you are interested in working with us, please send us an email. I'll be around, so you can just poke me, and I will get in touch with our HR. And without further ado, today we have Madrid DevOps. Do you want to present? Okay. How Mapbox is scaled over 9 data centers by Johan from Mapbox, right? Okay, here you go. You don't have. You want to run that?
I think this is also. Okay. Hola, soy Johan. No hablo en español bueno. Lo siento. Creo que con luz es mejor. Okay, but now I speak in English. Is there anyone who doesn't understand English well? Okay, if I speak too fast or if I use words that don't make sense, please raise your arm and I'll explain, and I'll try to speak slowly. Otherwise, I'm going to speak really fast, because when when I do a talk, I usually speak really fast. So I'll try to do it slowly. Okay, so I'm Johan. I work at Mapbox for a year now, and I'm from Berlin. I'm based in Berlin, and for the last month I've been in Spain. So I've been traveling because most of our offices are in the US, so in San Francisco and Washington DC, and yeah, we have remote people in Europe as well. Before working at Mapbox, I worked as backend engineer at SoundCloud, which is an audio sharing platform that is very big and has its offices in Berlin. So in this talk, I'm going to first explain what Mapbox is, which is important to understand, like the scaling decisions that we made. Then I'm going to explain what 9 data centers would mean, and how we ended up with these decisions. And then we're going to trace a request for a map from the browser of a user to coming to the actual source of truth. So, who knows Mapbox already? Okay, so we make maps for your websites or your applications. We make political maps, we make thematic maps, we make maps of streets and maps without streets, we make maps of mountains, we make maps of oceans, but not the ocean ground, sadly, yet. The cool thing about Mapbox is that you can customize the map that you're using in your website or in your application very well, and we give you the tools to customize the maps so that they fit to your application perfectly. One example of a website that uses us is Foursquare, which is a location service that helps you find points of interest around you. So here I searched for coffee in Berlin, and it displayed a map. And this map was styled by the Foursquare designers to exactly meet the needs of the Foursquare community. Certain points of interest that we usually display were removed. The color scheme is theirs. For example, they also made public transport smaller because they didn't want public transport as like the most important thing on that map. Another user of us is Runkeeper, which is a fitness tracking app, similar to Strava or MapMyRun, where here I recorded a run I did in Washington DC, and so you have it like in your phone, in your pocket on your phone. It records a trace, so every second it takes a waypoint, and then it can display it on the map again. And when I look at the runs I did, it's very important that I can see them on a map, because I want to know where I ran. Also, Runkeeper has the functionality of sharing runs with other people so they can follow them, and for this you also need to look up where is the run. So the map is an integral part of the application, and we make it very easy to put this into your application. Okay, so 9 data centers. So when I say 9 data centers, then this is like maybe the come down. It's like, oh, we run on AWS. Who runs on AWS? Okay, so about a quarter. Okay, then I can tell you something new. Cool. So AWS is a cloud hosting service. They host the physical hardware and have APIs and abstractions on top that make it possible to run your applications there and all your services. And AWS has the concept of regions, which are autonomous, logically separated entities of their data center infrastructure. And basically when you log into your AWS account, you can see them when you click on the top right. There's like a drop-down menu, and it's all the 9 that currently exist. This information makes most sense on a map, which is why here's a map with a bad color scheme for presentation, as I realize now. More contrast would have been better. The regions are spread all over the world. So there's 3 in the US, 1 in South America, 2 in Europe, and 3 in Asia. And all of these are kind of the same, they're all a bit different, but eventually they offer you the same services, and you can run the same applications on them. So why would you do this? Why run in many regions? Who else runs in many regions at the moment? 1. Okay. Who else runs in 1 data center? Wait, what do the other people do? Who runs things on their laptop? Okay. So, yeah, why do you want to run in many regions? It is definitely cheaper to run in only 1 region, or 1 data center for that, if you don't run on AWS. It's definitely way less complex, you have less moving parts, and it's easier to build. 1 data center is better if you just need to get started, and this is also what we did up until, I'm not sure when we made the switch. I think 2 years ago we started to add the first new regions. So before we were also just 1 region. But we had two reasons here. The first one is high availability. We have to deliver, we have to be robust, and the second thing is low latency. So, high availability. Basically, when we fail here, I get a page on my mobile. So my mobile starts ringing and I get an alarm. Probably others of you have the same experience. This is something we want to avoid. Also what happens is we post on this on status.mapbox.com. And so here, when I took the screenshot, everything was okay, which is good. Everything's green. But obviously, we need to always deliver the service to our customers. If you think back at the example with Foursquare, where they had the map with all the coffee shops on there, if you're searching for a coffee shop on Foursquare and you don't see a map, you will likely not continue. You don't know where the shops are. We're critical for their applications. With Runkeeper, it's not so bad, because if you can't see a run, okay. Still, obviously, we want to deliver a good service there. So we need to be up. In our terms of service, we have an SLA of 3 nines, which means that, I forgot the number again. There's so many minutes in the month that we can be down. It's not enough that if I get a page, I cannot look at it. Like, I have to look at it because there is response time. If something goes wrong, we have to fix it right away. So what's the things that are against high availability? The first thing that impacts our availability most is AWS problems. So the last time this happened was 3 weeks ago. DynamoDB was down in US East 1, which kind of brought down the whole US East 1 region. You couldn't scale applications anymore. You couldn't scale new instances up. You couldn't even see how many instances you had. It was quite a disaster. Also one of the biggest outages that AWS had this year. And for us, this meant we have to do something. And what we did there is we routed traffic away from the region. Question?
How long did it last, the outage?
So, I'm not 100% sure. I think the outage started and was finished in 8 hours. It's like, it wasn't a total, it was degraded service. So, if I remember correctly, the post-mortem that AWS posted, their internal DynamoDB tables that keep the state of their own cloud was under-provisioned, had problems serving requests, and then some of the requests failed. So not all of them.
Your own degraded state?
Our own degraded state depends again, because we have a lot of different applications. The first thing that we immediately looked at was map serving. I think this was like 20 minutes that it took us to go from something's wrong to, for most of our customers, this is resolved. US East 1 is our second biggest region after EU Central 1, so this had an impact. Luckily, this happened at night, so there wasn't that many users on there. It also impacted other regions though, because we used US East 1 as the main table, DynamoDB table. Later on I'm going to talk about our database setup. What we did is we had to fail over our primary database to another region. But since we had a replica running, this was fairly easy to do. So I think 20 minutes was the turnaround. But then we had other services, so we had the geocoder, we had directions that took longer to recover, because only then we started looking at these. And maybe in the end we can discuss the actual process of failing over a region and how this works. Okay, so the first thing, AWS problems. This happens, and you have to build for this. AWS does not promise that it will never go down. It will go down, and it's our responsibility as users to mitigate this with the tools that they give us. The second thing is, obviously our software has bugs, and the one thing is running software that is buggy, and the other thing is doing configuration changes that sometimes are hard to test or to stage. So what we sometimes do when we have critical deploys or we have critical changes, we just do them in one region that is currently in the night and doesn't have that much traffic, so it's kind of our way of doing red-blue deploys as well, but doing very slow red-blue deploys. We have not that much configuration that happens on the overarching layer over the regions. So basically that's only DNS configuration. The last time I fucked this up was 1.5 weeks ago, where we had, I think, 20 minutes downtime on One Direction stack because I made a copy and paste mistake on a DNS record. And we're working on fixing this. This never happens again. Okay. So AWS problems, Mapbox software problems or configuration problems, and the third one is critical deploys. So there's things where the best example here is changes to the underlying network structure. We have to change the subnet configuration. This you cannot do when you're running a workload on this. So what you have to do is you have to take the whole workload off, then you can do change, then you can put the traffic back on it. You can do this within one region, but why would you run two workloads in one region? It kind of doesn't make sense. So with the setup of multiple regions, it's kind of organic for us to take the traffic away from a region, do the change we have to do, and then get traffic back on it again. For the time where we remove traffic, our customers will see higher latency, but that's okay because the service is not down, it's just a bit slower. Questions so far? Yes?
So you put down a data center, deploy the application and put up?
Correct. So so when we deploy, okay, there's two things here. The normal deploy doesn't have this. For a normal deploy, for a code deploy, we don't do this. We do this for critical things that we have to change in the underlying layers. This happens like every 2 months or something. This is not common. And it involves basically a whole day of an engineer working on this to go through taking traffic off a region, doing the change, and then putting traffic back on it. It's not something that we currently can do fast. So we totally want to avoid this. On the other hand, we also do this for testing different configurations. So for example, when we have a new instance type that we want to test for our main application, we just we have a new instance type that we deploy in one region and see how it goes there. And from the experience there, we can then check if we want to do it in the other ones as well. Okay, so the first thing was high availability. Many regions, better availability. Hopefully, depending on how you architectured it. Second thing is global low latency. So, when you have a map and you want to use it, you need it to be fast. And so this is a video I recorded with a bad internet connection. As you can see, this is not fun. When you zoom around, when you pan the map, the tiles have to be there immediately. The map has to be there. And we're talking about something like 200 milliseconds, 300 milliseconds. The problem with this is that you cannot beat the speed of light. So, at least not yet. Quantum computers, yeah, it's coming. But so far you can't. A ping from here to Tokyo is 500 milliseconds. So we could not deliver a good service to everyone who's like further away than X from our data center. But yeah, latency is critical. So the only way we can solve this is to bring our data closer to our users. Okay, so that's what I'm going to talk about now. Questions so far? Cool. So this is the diagram I'm going to talk about for the next 15 minutes. You're going to see this more often. If this doesn't make sense to you now, it's okay. I'm going to explain all of the steps here. Let's start with the first one. So the user and the browser. When you have a map, let's take the example of the browser. Your users, you build a map, your users open it in the browser, and they want to see this beautiful map. It has to come from somewhere. The first thing that we have to talk about for this though is, what is a map exactly? You guessed it, right? Okay. Imagine the world. If you look at the world from very far away. Oh, is there map geeks here who want to talk about projections? Or okay. We're all Mercator. We do web Mercator. This is our view of the world. It's not correct. There's no correct projection. It should be a globe. Anyways, so you take the world, you zoom out. In zoom level 0, which is all the way zoomed out, you can see the whole world. And the more you zoom in, the more kind of detail you get, the higher the zoom level is. And we have to figure out how to represent this detail. Because obviously in this view, you cannot have Granvia represented as a data point. Like, you would have too much data. It would be, the whole planet would be loaded into your browser. So you have to have some sort of cutoff with the detail you show. And the detail we show is first by zoom level, and the second is by tiles. So there is a grid layer over here, and every tile in here can have a coordinate. So the tile up there and left up is like 0, 0, and then it's x and y coordinates. And it turns out that with these tools, grid over the world, every cell of the grid is a tile, and having the different zoom levels, we can actually identify every point in the world and every level of detail and where this is in the world. Should have put a URL in there. Yeah, but so this is the 3 parts you have to remember. The zoom level, for example, yeah, zoom level 0 is the world, zoom level 13 is a city, so this picture is zoom level 13, basically. And then you have many tiles to match the viewport of what the user now wants to see. So if I make the browser smaller, I have less tiles to show. If I make it wider, I have more tiles to show. If I pan around, I have to load other tiles. Okay, so the browser, before the browser can load the tiles, it has to load some JavaScript to show the tiles. And we have Mapbox.js that allows to do this on your website and to customize the map as you need it. So the JavaScript then determines the viewport, what part of the world should be shown at what zoom level, and then it goes and requests all the individual tiles. And that's the request we're going to deal with here. So here's one of the URLs that would happen then. So it's tiles.mapbox.com API version, the map ID, because it's your map and it should not be my map. The zoom level, which 17 is very close, and then the x and y coordinates. And these are PNG files. Here, they could be other formats as well. So this is raster files, it's image files, but it could also be vector tiles, which are a different format and are differently rendered. And then the access token to figure out if you're allowed to do this request. Okay, so that was the browser. We're doing a request now. The first thing that happens is that this request will hit our CDN. So first it will do a DNS query, and then it will come to the CDN. And CDN stands for Content Distribution Network, and it's a physical cache close to your users. We are using AWS CloudFront, but you could also use Akamai or Fastly or Cloudflare. There's a lot of these out there in the world. They all kind of work the same way. CloudFront has... okay, this map doesn't work. So imagine there is a map of the world, as before on zoom level 0, the outline, and then there's white points on it. And each of these represents one point of presence or edge location, so one data center by CloudFront, near to the users. And you can see there's way more here than the AWS regions were. So CloudFront, I think, has 37 edge locations and 9 regions. I think Akamai has even more edge locations. The more, the better, basically, because speed of light. And when the CDN now becomes a request, the first thing that happens is DNS, and we're finding the nearest edge location. This is some magic I'm going to talk about later again, in terms of how do you find the nearest edge location. Then we terminate TLS. We try to do everything at Mapbox on TLS, because we want to protect the privacy of all our users. If a bad actor is able to capture traffic that is in HTTP and that is location related, they can figure out what locations a person looks at. And this is information that should be protected. So I think we have some legacy APIs that work with HTTP, but most of the APIs are HTTPS only. So we terminate TLS, which also means that CloudFront has our SSL certificates. I'm happy to discuss afterwards how fundamentally broken TLS is, SSL is, and encryption on the web. SSL is terminated. The next thing is we're matching, CloudFront matches, they call it a behavior to an origin. So they look at the path and they figure out which server should this request eventually go to. And for each of these behaviors, so you can think of, like, for example, we have titles at mapbox.com/v4 and then the location, so that's one behavior, but we also have api.mapbox.com/directions, which is another behavior, and geocode, which is another behavior. And all of these have their own cache configuration and have their own origin servers. So we're looking in the cache, and this is the big thing that the CDN actually does, it caches. So it looks in its own cache based on the URL and the query string and sees, is there something on this edge location already or not? If there is, then return it. And this is like the fastest we can get at the moment. You go to an edge, if you're in Madrid and do a map request, you will go to the CDN edge location in Madrid first. And if that has the actual tile that you are requesting, then you will get a super fast map, where that tile will load really fast. CDN works best if the cache is full. So the more tiles that are cached, the better it is. Every cache is individual to each edge location, so they're always local. And kind of the best thing would be whatever the CDN ever sees will just be cached. But the problem here becomes stale data. So if I have a map and you're looking at it and it has a blue ocean, and then I realize blue oceans are not cool, purple oceans are cool, and I change this, all the tiles that the CDN would ever have seen with the blue ocean would still be served, because how would the CDN know that the ocean is now purple? So we have to remove stale data again, and this is a trade-off between the high cache hit rate. You want as many things as possible in the cache, and the update delay. If I change something, when is this going to be available in the CDN? And currently we use time to live here. So every object that you put in the cache expires after 5 minutes, which eventually gives us a cache hit rate of around 35% here. We are experimenting with different TTL values, and we're experimenting with cache invalidations, but yeah, I'm happy to talk about trade-offs afterwards. So we're in the CDN. CDN has a cache miss. We go down further in the stack. We were with the user in the browser, went to the CDN, nothing there, we have to continue. Now we go to the actual regions. So before I said there's this magical thing that you get routed to your nearest edge location, which is something that CloudFront built and they don't really talk about it, but it's also exposed by AWS as another service, which is called Route 53, and I just expect that it's the same technology behind it. So DNS originally is the thing that makes 20.com be an actual IP address that a server can reach, that a client can reach, so the server's IP address. But the cool thing you can also build on top of this is to route you to the server that is best for you. And best for you, in this case here, means the server with the lowest latency, the lowest historic latency. We're using Amazon's Route 53, but this could also run on DIN or EasyDNS or Akamai. They all kind of have similar offerings here. And it routes us to actual regions. So imagine again you're in Madrid, you do a request in Madrid, first thing you go to the Madrid CloudFront edge location, it has a cache miss, then you probably will go to Frankfurt, which is the nearest. Maybe also Dublin would have better ping. I don't know. Who knows? You never know how the internet routes you. Could end up in the US. Okay, so now we go into an actual region. As I said, there's 9 of these. They basically all look the same in terms of the infrastructure. The first thing that you're always going to hit is the load balancer there. So the load balancer routes requests that come in to application servers. And it's the entry point to a region. We're using Elastic Load Balancer, which is a product by AWS. If you want to run open source, then AJ Proxy or Nginx could serve this for you. If you want to have a physical device, F5 might be right for you. But they all do the same. Request comes in, and you route the request, proxy the request to one of the other application servers that are behind it. Before this happens, we terminate TLS again. Same thing as with CloudFront. The query from CloudFront to the actual region is going over the public internet. We cannot assure that there's not going to be a bad actor in there, so we have to do TLS again to protect the privacy of our users. Then the load balancer determines which application server to use, and the first thing here is always only take healthy servers. So the load balancer will do health requests to the application servers. I think we use every 30 seconds. We query the status point on our application servers that checks if the database connection is still working and checks if the application is still running. If 2 health checks fail, so after 1 minute, an instance is unhealthy and will be shut down, and a new one will be started to replace it. If there's many healthy instances, for example, if there's 20, then the ELB will route to the one that has the least outstanding requests. So imagine you have 1,000 requests coming in. Every application server needs 1 second. There's going to be a lot of requests that are piling up. So the ELB always tries to take the one that has the least ones going at the moment, in the hope that all requests take the same amount of time. The load balancer will wait for the results and then return them back up. Questions so far? Okay, so we're here now. We're going down to the application. Application servers. Back in the days, we would have run physical servers. These times are over. Everyone is running virtual servers. Even if you're having physical servers at home, we will likely run virtualization on them. Amazon's EC2 is the thing here, but you can also run this on Google Compute Cloud, Rackspace, DigitalOcean. They all have similar offerings. You start a machine, you can SSH into it. It has open ports to the internet. We are running so-called C3 X large instances. At the moment, I think these have 2 or 4 cores, I'm not sure, and like 2 or 4 gigabytes of RAM. We're actually experimenting a lot with different instance types, because all of the instance types have, for one, different performance characteristics, but also different price points. And yeah, we're very open to experimenting with these types. Also, with different regions, we are sometimes using different instance types. But recently we switched down to X larges. We're running Ubuntu Linux, and we're build our application in Node.js and Express. Okay, so request comes in, and the first thing that has to happen is we have to authenticate. If you remember, there was an access token in the request, and we check this access token and check if the user is allowed to do this request. Then, when the authentication is valid, we go load the map data to figure out where are the tiles that we should load for this user. Where is the actual map data coming from? And then we fetch this tile and return it. And so let's talk about databases. DynamoDB is the thing that 3 weeks ago went down and caused us trouble. Luckily, we didn't run DynamoDB just in one region, but we are running it in several regions. So we built a primary replication scheme for DynamoDB, which we also open sourced, which is based on a Kinesis stream that DynamoDB generates and that you can consume. And yeah, so we're running a primary in, at the moment, US West 2, and replicas in US East 1 and in EU West 1. When a read request comes in, then the region will go to its nearest replica. If the nearest replica is the master, it can also go to the master. And writes can only go to the primary. And from the primary, then we use DynamoDB streams and Lambda to replicate it again on the replication, on the replicas. This is a scheme that worked okay for us. We are able to detect problems with the replication, and we're able to replay certain parts of the replication again. And we have built this in a way that it's idempotent, so we can rerun streams and it will still work. On the other hand, we're also not having a high write load because we don't have that many customers who change maps, but we have a lot of users who request maps. So this scheme is actually biased towards this business case that we have. Also, we do caching in instance, and this means that we furthermore reduce the amount of database round trips we have to do. Happy to discuss more afterwards. Okay, so we went to the database. We know this is like well authenticated. We know that the map is valid. We know the location of the map tiles. Maybe quickly, map tiles, there's many different formats. There's some tiles that we basically have the whole tile set on S3. There's some tile sets that we have to fetch several tiles to combine them on the fly on the server. So this highly depends on how the map is built by the user and how it comes to our servers. And yeah, eventually though, what happens is that a request always has to go to S3 here. So S3 is not the fastest. Like, it's fast, but it's not always the fastest. It turns out that having a Redis cache that is living near your virtual machines in the data center is faster. And what we do is we do a race when we want to fetch a tile. We go to the local Redis instance, but we also go to S3 at the same time, and we return the information from wherever it's fetched first, returned first. If it's found only, or no, in all cases. So we always go to both. We return from the one that is finishing first, and then we write the information from the S3 to our cache. So we always update the cache on every read, which means that we have the exact same read and write load on our cache clusters. In this way, we make sure that the cache is never stale. And you might get stale data once, but you will not get it again. So, have you tried reloading? Oh yeah, the problem is fixed. Perfect. When you have a lot of users, this is not a problem. Also, we're using Redis as a least recently used cache, which means that like the Redis instance only has so much memory. We're currently using R3 4x large instances, which have 122 gigabytes of memory, and like at some point this is going to be full. And when it's full, what we do is we throw out tiles that have not been requested in a long time. And this assures that popular tiles are always cached. And there's something here that really helps us. It's the fact that people always want to look at the stuff around them. So Europeans mostly look at Europe, and people in South America mostly look at South America. And this means that a lot of the tiles will be there in the cache. we get an 80% cache hit rate, which is phenomenal. Which is really, like, we're a bit wondering how we got so good. Maybe it's a bug in our monitoring. Okay. Also, so a tile usually is around like 10 kilobytes. It's like one PNG file. So you can fit 12 million. Is that right? Tiles in there? Into the cache? Yeah. So a lot of tiles can fit into this memory. Also, there's one more bigger instance we could use on AWS, the R3 8X large with 240 gigabytes of RAM, and you can shard Redis as well, which is something we haven't done yet because sharding is always a bit complicated. But this cache can basically scale infinitely, which is very cool. Yes?
So if you take as a basis a 10 kilobytes tile, if you take all the levels of zoom and all locations for a given map, roughly what would it cover?
So the question is, how big is a map?
Yeah.
I don't know. I'm sorry, I don't know. I should look this up. I should figure this out. The world has a lot of oceans, so it's definitely not the kind of the mathematical size. There's a lot of no data that you would never cache, right? Because nobody looks at oceans. But yeah, I cannot tell you, sorry. Okay, and this, so this was the whole pipeline now. When you're done, when you're going to S3 eventually, and it bubbles up again, the map is shown. Okay, so what did this bring us? Because that's an important thing. Fuck. So the first thing is, what I talked about before is the fact that this brought us better availability. And when there is an event, when we have an outage, it's usually contained within one region. It doesn't spread over other regions. This is definitely a huge benefit. The second thing is latency. So here what we did is we took a sample from our CloudFront logs, from our edge location logs, and we looked at how long does it take to go to the origin and return. And okay, maybe it's really okay. So this region here is red, and now it's green. Now it's red. Now it's green, which means that red means it takes longer than 300 milliseconds to load, and green means it's faster than 50 milliseconds to load. And here we, before what is like only the green clusters, we only had 2 data centers. We had one in Europe and we had one on the east coast of the US. And afterwards it's 8 data centers, because Frankfurt wasn't open back then. And we basically get better latency all around the world. The only place where we have bad latency still is China, which is kind of its own beast, and India, because India is too far away from all the other data centers. So this will change. AWS is going to have a region next year in India. Surprisingly, South Africa gets good pings. I guess this is because they're going to South America and have a big pipe. Okay, that's it. Thank you very much. Muchas gracias. Preguntas, por favor.
When you were talking about state data, you mentioned that you use TTL to having state data. How do you handle the problem of having, for example, 2 different tiles with different styles?
Sorry, having?
2 different tiles with different styles. For example, two tiles that are together with different styles.
Yeah. So,
I mean, I believe that TTL is different for every type.
yeah, okay, so the problem is you have one tile that is cached, you have another tile that is not cached, and the user scrolls on the map and sees one tile with a blue ocean and one with a purple ocean. This is a problem we don't fix at the moment. This can happen. Luckily, in our use case, this is very, very uncommon for two reasons. One, usually the fragmentation of the tiles is not that big. So it will be kind of like, it will be a person that has panned there lately, at least for the popular spots. Second, people don't do drastic changes to their maps. So even if you get a stale tile and a fresh tile, the change is likely going to be like marginal. It's going to be like the street has changed a bit. When people do really drastic changes to their maps, they create a new map that, by having our customers submit patches to our internal systems, by having other people work with us on these things. Our whole GL rendering stack is open source. And this, for example, led to our competitors starting to do pull requests on our stuff, which is great. The things we don't open source is CloudFormation templates, is yeah, our internal application logic around authentication, and there's a lot of things that kind of don't make sense to open source just because they're so specific to our architecture. It's always a bit like when you're writing infrastructure code, it can become dirty in a way that it's very not generalized and it makes no sense for everyone else. So we're better on building libraries and open sourcing them than building kind of tools that other people can just immediately run.
You were talking about a lot of hoops to jump through. So how does it come about? Does it start from the developers, or how would it typically happen?
Hoops for what?
For I mean, going open sourcing a project or
okay,
library.
So yeah, okay. So what's the hoops between open sourcing an infrastructure tool, like we're writing it and then we want to open source it. It doesn't work if you write something and then you open source it. Like you have to write it open source from the beginning. When you create the repository for the tool you want to write, it needs to be open. And this is the trap we ran into so many times with our infrastructure tools. The thing we built that is very specific to us is we built Mapbox CLI, which is our internal DevOps CLI tool that every developer has on their machine. It does authentication, so we have two-factor authentication on everything we do, all our developers do, which gives me really good nights to sleep because I know if somebody loses their laptop, then our data center is not compromised. And it has kind of our logic for deploying and looking at logs from Sumo logic and so on and so forth in there. It is a big potpourri of things that are only slightly usable for other people because they encode our names everywhere. Like we have our namespaces in there, and we started trying to generalize it, and it just took forever. And then we stopped because it was too much. The thing we open sourced though from that tool is some libraries that are facilitating the interaction with AWS. So we have a tool that is called cfnconfig that helps you to push templates, CloudFormation templates to AWS and change them there. We have a tool that is called cfn event stream that can pull CloudFormation for the logs, so you can stream logs down. And what else did we open source? We open sourced our replication engine. The database replication, and the common theme that we have with services that we open source is that we have a library, and then we wrap the library into another project where we have all the Mapbox specifics in there. But the core part is, if you don't open source it from the beginning, you're going to have a bad time. And this, yeah, sadly the state with some of the things we have. Okay, very last question.
It were three questions. by the way. The first one is, have you considered to use the Spot instances, or are you using it? Another one is, I think you are making rich Jeff Bezos more than he is now. Are you thinking about using another cloud platforms besides Amazon? And also, how do you handle if you have to do some rollback? Does it have to do something on S3 or not?
Okay. Spot. Are we using Spot instances?
Are you using?
Yes, a lot, because the things we run are expensive, specifically in the processing. As I talked earlier, we have kind of big processing pipelines where we ingest a lot of data and then tile it and put it on S3. And for this, we're like running thousands of instances, like literally, like we can scale up to more than 1,000 instances. That's very expensive, and Spot instances are around 1/10 of the price. And basically, without Spot instances, we couldn't do our processing because we don't have enough money for that. Like we have money in the bank, yay. It's not enough for running the things we want, meh. But with Spot, it definitely makes it better. We experiment with using Spot for APIs. Basically, the idea, you have load, and you need for a certain capacity to fill this load. And then you have like the capacity you have as kind of a buffer for what if a peak happens. And we want to fill this peak with peak capacity with Spot instances, and then be able to, we want to fill that. If the peak happens and it hits our capacity limit, we need to be able to still scale up on-demand instances really fast, and we need to be able to, when Spot instances die, to scale up new instances really fast on demand. There's problems there, specifically with the speed of CloudWatch and autoscaling. So CloudWatch, I think the smallest granularity is a minute, and that's just too slow. Like we can't do good spike analysis here. We can start instances in like 20, 30 seconds if we really try hard, which is actually like nearly as fast as, or it's not as fast as a Docker container, but it's still like reasonably fast to react to a change in load. But so far these experiments have been okay, but not overwhelming. For processing a lot, every queue that we have runs Spot. I forgot the second question already.
Using another cloud platform.
Yeah, using another cloud provider. Yes, we would switch, but there's no need at the moment. My feeling is AWS is steps ahead in terms of all the products they have, in terms of the processes they have established. Google is doing great work with Google Cloud, Compute Cloud, and it's going to be interesting what comes up there next. It definitely makes it easier to just run everything on AWS, since they have all the tools we need at the moment, and everything works together quite well. So the friction within the platform is fairly low. Also explaining to my developers how, like, what the all the lingo that AWS has, and explaining kind of the world there is actually not that bad, because the documentation is always great. They have a lot of training material available, and it stays in the scene. Whereas the moment you go out of that, you confront them with even more complexity that will not have the same ways of getting to know the complexity. The third question.
If you have to do a rollback of deploy.
Okay, a rollback. So I mentioned before we use CloudFormation for deploying new code, and we're using a strategy that it's called rolling update, but we don't use it as a rolling update. We use it as a red-blue deploy in a way. So we imagine we have 10 instances that run the old code, new code comes in, we start 10 new instances, so we over-provision double, Wait until the new instances are all healthy and then the old instances are terminated. This is something that AWS provides for us. It's update policy rules in auto-scaling, and it's the rolling update group that you can use not as a rolling update, but also as a red-blue deploy. The rollback here happens if the instances don't come up. So if the instances aren't happy, which usually is happening because the code is faulty in a way, then all the new instances will be shut down again, and the old instances continue to live, and the users never see anything. We can only deploy this way because of elasticity, because we have an unlimited amount of instances on AWS, which is not true. We see the limits, but they're still okay for us.
You never had to roll back something that came up after the red instances were killed.
Okay, did we ever had to roll back when kind of the new instances were in service and the old instances were already killed? Yeah, but then we roll forward and do a new deploy. The easy thing here is always to deploy the old code version, which hopefully will boot again. We've seen this problem often in the past with external dependencies. So npm goes down, GitHub goes down, canonical apt mirrors go down. S3 happily or luckily doesn't go down that often. So that source of boot errors is disappeared. Okay, over. Muchas gracias. I think we'll have drinks in some way or another. I'm going to be here. Oh yeah, tomorrow there is the Geo Developers happening, the user group. And I'm going to be there as well, talking with Esri and CartoDB about the state of web mapping, and we're going to talk way more in detail about what does GL mean, what are raster and vector tiles, and how will web mapping evolve. You can still join geodevelopers.org. Thank you.